Okay, let's continue with the directional derivatives topic. And just as a recall, we had that differential of z, which is the amount of change in the curve. You remember we have that surface and that curve, and we were changing the height of the curve according to the displacement in the direction of h, and h was a distance. So what we need to calculate is the change of this, because let's say this is point A and this is point B, and if you draw a flat line here, this difference is the difference or the change on Z. And we want to know how the change in Z is in this case is an effect on of the change in H. Okay, so it is the same that we have some Z point here and Z sub 0 divided by H, because we are interested in get the change on Z while we move along H. Okay, so we can explain this in terms of the definition of the differential calculus, the way that we are going here to explain. So this is some f of x sub 0 plus h times a, because this h times a is one of the sides of the triangle that is defining the unit vector u, and y plus h times b. This is certain amount of x direction plus certain amount of y direction. And this is the difference between this definition and the regular standard definition for the um, differentiation. And this distance minus f evaluated in x sub 0, y sub 0 divided by h. Okay, so this is kind of the formal definition of the directional derivative, but this is in the general form. So if we take the limit of this h as approaches to 0, we get, if the limit exists, we get this. And this is the notation for the directional derivative. It's capital D sub u f of a variable evaluated at x sub 0, y sub 0. And this directional derivative is equal to the limit when h is approaching 0 of this guy over here. And remember that we are adding only this component of x and component of y to the general expression, because we are not moving exactly in the x direction or in the y direction. We are moving a little bit in x and a little bit of y. And this is going to be the end point, and the first point is going to be this f evaluated at x sub 0, y sub 0 values. Okay, well, doing some arrangements here, because we know that z is a function of the curve along the h axis, being this h axis any arbitrary vector. We can define our formula for direction like this. We can have this d, capital D sub uf, which is the directional derivative of the function of x and y, is going to be equal to the partial derivative of x times a plus the partial derivative of y times b. And a and b are the components of u. Okay, this is only a simplified form of this HA and HB. This is going to be A and this is going to be B. Okay, this is only to simplify the terminology so we can have a constant here because these components A and B are the components of the vector U. And from your vectorial calculus class, you know that components on X and Y is going to give you the direction and the magnitude of the unit vector. So this is the only way that you can, if you have a reference plane like the y-x axis, the only way that you can have or know the direction of this and the magnitude of this is by knowing its components. So we are adding this trigonometric component to our partial derivatives because we need to know how much is moving in the x-axis and how much is moving in the y-axis. Okay, and we are transforming that to this unit vector which components in x and y are these two amounts that are noted there. Okay. Okay, so let's find the directional derivative of this. Let's work an example, and let's work this d sub u of x of a function of f x and y, and let's say that this function is equal to x cubed minus 3 times xy minus 4 times y squared, and this is the function, and the vector u or the directional vector for this is given by an angle theta, which is equal to pi over 6. And then the question is first is what is the partial derivative of this function? And if the vector u has an angle of pi over 6, what is the directional derivative evaluated at 1, 2? Okay, so let's work let's work out this example. We're going to need to redefine this. This is the general form, but we need to keep a little bit of clarify work to these A and B components. You know that this A and B are the components of the unit vector U, but here we have this little amount of A, a little amount of B. If we say that this is A and this is B, and the unit vector equals 1, we can say that the A, let me write it here, up here, because we are running out of space. A is going to be equal to the cosine of the angle, and B is going to be equal to sine. Okay, in this case, because vector unit is equal to 1, it's a unit vector, and if you do the math here, you will come up with this expression. So with these two functions, you're going to be able to find the direction and the magnitude of this, of any other operations related to this hypotenuse of this unit vector that is giving the direction to this uh, partial derivative. Okay, so if we rewrite that, we will come up with this, which is capital D U, which is the directional derivative of this function x comma y, is going to be equal to the partial derivative with respect to x evaluated in this times the cosine of theta plus the partial derivative with respect to y evaluated in this times the sine of theta. And why this cosine and sine? Because here you know that to have this directional vector explain or define, you need, if you know these relationships between these two and this according to the angle, we have the angle here, which is pi over 6, and you have all the recipe that you know you need to calculate the direction of this uh, unit arbitrary vector. Okay, so work it out, the example again. Let's say that d sub u of the function x comma y is going to be equal to the partial derivative of x of the xy function times the cosine of pi over 6 plus the partial derivative with respect to y of these two variables times the sine of pi over 6. Okay, um, doing the math there, this is equal to, let's write it here, this is equal to 3x squared minus 3y, which is the first partial derivative of this with respect to x, and the cosine of this is equal to root square of 3 divided by 2 plus the minus 3x plus h times y times 1/2, which is the sine of the angle of pi over 6. Okay, if we simplify this, we can have this halves out of the expression, and we can have this 1/2 times 3 times 3 square root of 3 x squared minus 3x plus 8 minus 3 times square root of 3 times y. Okay, okay, and that's it. This is the general expression that is the directional derivative for this function in the direction of the unit vector with an angle of pi over 6. And if we do the substitution, because we are required to evaluate the directional derivative in these values, then we will see that capital D sub UF evaluated in 1,2 is equal to 1/2 times 3 times the square root of 3 times 1 squared minus 3 times 1 plus 8 minus 3 times the square root of 3 times 2. And that is equal to 13 minus 3 times the square root of 3 divided by 2. And this is the result of the directional derivative evaluated at 1, 2. I am not going in detail with this, but because I'm writing there step by step, you have the time, you can check the numbers here to see if they are correct. Um, it is because we are now at the next level of these calculations that we don't need to go deep in detail. We already have um, performed a lot of the partial derivatives. So in this case, it's not that hard to get all these results. We are only substituting. So if you want to confirm and validate, you can practice here. And let's see if we need to work another example or something. But at this time, this is how it's done for the directional derivative of a function in multivariable going not just in the y or on the x-axis direction, but in any angle that is giving the direction to this vector. In this case, the vector u. You can have this vector u direction using how much is moving in x and how much is moving in y, and adding that to this expression so you can have the partial derivative in that direction.